Hey, Math 30-2s, how's it going? So we are going to start our new unit or new chapter today. It's a pretty easy one. I think it's a pretty easy one. Pretty straightforward. It's called polynomials. In previous math classes, like Math 20 and Math 10, you talked about polynomials already, or very specific types of polynomials like linear functions and quadratics. We're going to expand upon that, and we're going to talk about different types of polynomials that go beyond quadratics, that have cubes and powers of 4s and powers of 5s in them. So the first thing we want to talk about is what exactly is a polynomial? So a polynomial is just something that only has multiplication, addition, subtraction in it. Those are the only operators that are in there. There's no to the power of x in there. There are, what I mean by multiplication, you can have a multiplication of x's like x times x times x, which gives it x to the power of 4, but you won't have like 2 to the power of x. You won't have any square roots in there. All your exponents have to be whole numbers. They have to be nice numbers. They can't be negative numbers. You won't have like a divide by x or anything like that. Right? It's a pretty simple thing to talk about. It's like, so a polynomial, if I just want to think about general polynomial, so this is a function notation. I'm going to name my function f. So this is the name of the function, right? This down here, when I put in the brackets like this, it says f of x. The inside part here is the input to the function. What are you going to put into this function? What changes as you plot this graph on the x and y axis? Well, you put in an x value, and you get a y value out. You put an x value, and you get a y value out. So that's my input. You say this as, I'm going to say it a lot of times, you're going to say this as f of x. So that's how you would say that. Now, to be a polynomial, so to make sure that this function is a polynomial, because we're talking about functions here, to make sure this function is a polynomial, you're going to only have your coefficients, the numbers in front. So like in these examples down the bottom here, or the next part here, your coefficients, we'll just call that a. This kind of number could be any number you want it to be. So this could be a real number. Right? Then it's going to be times x to the power of n. Now n has to be a whole number. Remember what whole numbers are? The numbers that don't have decimals. There's numbers that don't have negatives. They're just like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And they have to be numbers. They can't be other variables. Right? And then you would just add or subtract another coefficient and another x to the power of n. And then you would add another one at x to the power of n. And as n's could be different n values. Like if this first one was a 5, then this could be a 4, and this could be a 3. And then you can count your way down until you have just a constant value, like 5 or 6 or 0. 0 is a constant value, and they could all be negatives. Your a values could be any number you want it to be, so that a value at the end could be a negative number. Right? So these are examples here of polynomials. You could see that this polynomial is just the number 5. That's all it is. Right? It doesn't have any x. You could think of that x there. You could think of this having an x in it, but that x being raised to the power of 0. And if you remember some of your rules, anything raised to the power of 0 is 1. So this is just be 5 times 1, which ends up being 5. So that's this first example here. Now, because of that, because it has this x to the power of 0, which you don't see, you don't have to write it out all the time, so you can just write down 5. This says that this has a degree of 0. Now, the degree of a function is the highest exponent. The highest degree is the largest exponent of the polynomial. It gets a little bit complex if you have multiple things like y's, x's, and z's in there. But that's not a polynomial in our case. But right now it's just going to be the highest exponent. And even though you don't see the exponent on the number 5, you can write this in there. You can write this little extra piece in there, which gives us that exponent of 0. Right? These other ones are a bit easier. You can actually see them. Like if I was saying this 1 is technically 1 times x to the power of 0, but this 2 times x is 2 times x. And the x, if you don't see the exponent on the x, you assume it to be a 1. So x is the same as saying x to the power of 1. So this has a degree of 1. Now, the reason I'm talking about the degree, because the degree of the function tells us the shape of the graph, how the characteristics. Where does it start? Where does it end? Which way is it going? Is there a min? Is there a max? Okay. We'll get to those kind of characteristics later on. This first next one here, the highest degree of this one, you got 2, you got 1, you got 0, so the highest degree is 2. Next one is 3, 3, and a 1. 3, 3, and a 1. You can't see it, but it's a 1. Because the 3 is counted twice, technically you just rewrite this as 7x to the power of 3, because you can group your like terms, and our degree is 3. There you go. Okay, so we're gonna. This one's here. Okay, so we're gonna talk about a few different types of graphs. 1, 2, 3, 4. Yeah, but 4 different types of graphs. We're not going to go too much further than to the power of 4, right? We go up to the power of 3 pretty much. So these degrees up here, the 0, 1, 2, 3, those are the degrees of the graphs we're going to talk about. Now, a constant graph has a degree of 0. So that example, what we had before was x to the power, or x equal to 5. That's a constant graph. Oh, not x, sorry, f of x, I should say. Let's put that part in there. Which, we're going to talk about this later on, but f of x can be interchanged with the y back and forth. They're both the same thing. So I can actually say that this is also y is equal to x, or y is equal to 5, sorry, not equal to x. Okay, so what this means is that if I were to create a little chart, because I want to plot this out, I want to see what this graph looks like. So I'm going to create a little chart over here. A bunch of x values. I want to know what my y values are afterwards, so I can plot this out. I'm going to pick a bunch of random numbers like -2, -1, 0, 1, and 2. Okay? And I want to see what comes out. So I want to put a -2 into this equation. So my equation is y is equal to 5. And I want to put a -2 in here. So remember that this is x to the power of 0. That's what that technically is. I could just put that there because that's just 1. So I'm going to put a -2 in there, -2 to the power of 0. Now, what we said before, anything raised to the power of 0 is 1. Well, this would be 5 then. So if I put a -2 in, I get a 5 out. So I'm going to go here and put a -2, 1, 2, 3, 4, 5, and put a dot here at -2, 5. Okay, let's go and do it again. You're going to see a pattern really quickly here. If I put a -1 in there raised to the power of 0, well, -1 to the power of 0, well, that's just 5. Or 1, sorry. 1 times 5 is 5. Okay, so -1 is 5. Okay. If I put a 0 in there, 0 to the power of 0 is 1 times 5, which would be 5. Okay, put a 1 in there. 1 to the power of 0 times 5 is 5. 1 to the 2 to the power of 0 is, just get 5s out. That's why this graph is considered a constant function, because you only get the 1 value out. You just get the 5s. If I put any number, x value in there, I'd always get 5. So I get a bunch of 5s going across here. Get a bunch of 5s going across here. Then you pull out your drawing tool and you draw the graph. There it is. I'm going to just make that blue. No, actually, I'll make that red. So I got a nice constant graph. I'll put little arrows on the end of it to show that it goes on forever in both directions. So a degree of 0 gives us this kind of nice flat line at a constant value. So that's why we call it a constant graph. Okay, so let's do an example here of a linear graph. A linear graph has a degree of 1. We can use the example that we used in the previous up here, where it says 2x plus 1. Let's use that example here. Remember, I can just say that f of x is equal to y, so I can say that this is y is equal to 2x plus 1. I'm going to create a little chart here just to see what happens. I got x, I got some y's. I'm going to put some random x values in here. I'm going to spread it out a little bit more because my graph goes. I'm going to go, I don't know, let's go -4. Let's go to 4. -2, 0, 2, and 4. I'm just going to skip by 2, 0. Okay, so I'm going to put that into my equation where it says 2 to the power, or 2 times x, sorry, not to the power, 2 times x. So I'm going to put negative 4 in to start off with. Negative 4 times 2 plus 1. So negative 4 times that's negative 8 plus 1. So I get negative 7. So I get negative 7 out of this first one. So I put negative 4 in. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Right down here. So my first point is, when I say negative 4, negative 7. So you count over negative 4. 1, 2, 3, 4, and then you count down 7. All the way down. Okay? Just get rid of that. And put negative 2 in. I'm just going to write here on the side. 2 times negative 2 plus the 1. Negative 2 times 2 is negative 4 plus 1 is negative 3. So I got negative 2, negative 3 right there. Okay. Let's pick another one. I'm going to put a 0 in there. 2, 0 plus 1. 0 plus 1 is 1. Okay, so I get 1 right there. Okay, so I get, oops, I should put these points in here. So negative 3, 1. Now I can use these ones mentally. So 2 times 2 is 4, plus 1 is 5. 2 times 4 is 8, plus 1 is 9. So I have 2, 5, 1, 2, 3, 4, 5, and 4, 9. Okay, so what do you notice about these dots here? Are they are, oh, I have double-sided arrow here. I might as well use that. So these dots are straight, they're linear. It's a straight line right there. So I put that there. So that is a linear graph. It ends up just being a straight line. Remember that we did this in Math 10 when we went y is equal to mx plus b, and you get those straight lines. Okay. The next type of graph we're going to talk about are quadratics. Remember, quadratics have a degree of 2. So an example of this would be, and we can just use the example up at the top up here, 2x squared minus 1 plus, minus x, sorry. So 2x squared minus x plus 1. So there's a nice little quadratic. We can plot this out. What I'm going to do for this one is I'm going to use my graphing calculator to do this, rather than plotting it myself. Do mental math here. I'm just going to look at this graph. Here's my graph. So 2x squared minus 1x, I can call this f of x. Okay, there's my graph. Looking pretty good. I can also I can look at the table of this graph. Okay, so here's my table. So I got negative 2, 11. So I can plot some of these points out of my notes here. Let's find my notes. Oh, these are not the notes I want to look at. These are the notes. So what plotting points do I have here? So I have negative 2 and 11. That goes beyond my graph. I got negative 1, 4. Okay, so negative 1, 4. Oh, let me see what we have here. Oh, yeah, my scale's off on the bottom here. Let me just fix that. Yeah, so there's negative 1, 4. So I'm going to put that into my graph. Negative 1 and 4. Let's go back here. We got 0, 1, 1, 2, and 2, 7. If I can remember those. 0, 1, 1, 2, and 2, 7. Okay, and if I did negative 2, I'd have 11, so it's way up here. So this kind of graph has this parabolic shape to it. It's hard to draw sometimes. So it looks like that. Probably better if I had a better scale, but that's what essentially what a quadratic looks like. And a cubic function, we're not going to use this set. This one here is probably going to be too steep here. We'll just go with a typical cubic function of x cubed plus x minus 2 or something like that. Okay. So I go back to my graphing technology here, and I'm going to put in x cubed instead. There's my x cubed minus x plus 1. Is that what I decided to put in here? Oh, I put a plus. Plus x minus 2. I like the other one better, actually. It's very much nicer graph. Okay, so this graph looks pretty nice. So what I'm going to do with this, we'll just modify what we use for our graph here. We can erase some of this. Oh, come on. There. Okay, so I'm going to graph this one instead. Remember that this is also equal to y. So if you wanted to, you could put some random dots or points in there. And we can look at this. So we can see some points here, -2, -5. I'm just going to try to keep this as accurate as possible. -2, -5. So there's a point right there. -1, -1. -1, +1. Okay. 0, 1, 1, 1. 0, 1, 1, 1. Seems like I got a lot of ones in a row. They're all ones, one, ones, right? You notice it goes up and then down, then back up, and then 2, 7. 2, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so if I'm going to plot this out, it's going to go up, down, then back up. There you go. So that's your typical cubic graph, and these have a degree of 3. Other ones like quartic graphs and quintic graphs, they'll have different degrees as you go up. They have different shapes. Okay, so let's talk about the characteristics of these graphs in the next video. Might as well just do that. Just cut this one a little bit shorter, and I'll see you in the next video. Bye.